So we are now studying about the central limit theorem for sample proportions. So allow me to explain the concept in details about the central limit theorem based on our examples that we are walking through right here. So let's have a look at my first example, example 1, on the computer screen here. So example 1 begins with a description saying that business major is known to be 30% in the college student population. And part A now is asking, a sample of 40 college students is collected. Find mu p hat, the mean of this sampling distribution of the proportion. Find sigma p hat, the standard deviation of this sampling distribution of the proportion. And is this sampling distribution of the proportion a normal distribution? And so this beginning description of our example is important. It introduces us to the college student population. So the wording is quite clear here. Business major is known to be 30% in the college student population. And so obviously, and even before we worry about any of the question, either question A, B, or C later on in the example, but right here before any question is being drawn out from this population, we already had a known population. So in this population, we are looking at the category for business major students. And so business major is known to be 30% in the college students population. So here, back on my writing board, I can just now simply say that we have a beginning population. And simply here, because I am giving instruction as well as giving a step-by-step instruction, and so for that reason, I have to write down these optional steps labeling what we're looking at here as being the population, the beginning population. But when you're actually doing this on your own right here, then these steps are not necessary. So the beginning population is simply just the college students. And then in this beginning population, we're looking for a category. Because the idea now is that in order to have a proportion, in order to measure a proportion, we need to set up a category. We need to know what category we're looking for. So the category that we're looking for in our beginning population here is that we're looking for business major. And so once we have a definite category being the business major here, and we are particularly looking for this category in our beginning population, then here the beginning description gives us such an important information here. The business major is known to be 30%. So this is known to be 30%. So this 30% is currently in a problem being expressed as a percentage, but this is indicating that what we have here is the proportion, and further this proportion appears to be directly as a description of this beginning population. So I now can say that what we have here for this business major, what we have here is we have a population proportion, P equals 30. And so that's how I explain about we have a known population proportion. And for all calculations later on in the problem, we are going to be using these proportions in decimals. So I am going to put that 30% in a decimal, 0.3. But so once again, right from the description, the beginning description of the problem, then this population proportion, so here I'm labeling it, this is a population proportion. Another way to help in case anyone still struggling about how we can identify where it is to be a population proportion, then simply I can decide this proportion here to be a sampling proportion simply because it was given and without telling us how many students it came out from. And further, in this problem, it's making it even easier that it's a known proportion in the college students population. So the wording is quite obvious. But in case wording is not as clear as this problem right here, then you can rule of thumb here is that anytime a proportion, a mean value that came out, but without indicating for us how they came up with that, out of how many people in a sample, then highly likely it is a population value. And so here, even if we don't have this term college student population, we can still be able to decide that this should be a population proportion simply because it's simply just given and without indicating how many students it came out from. And then, as I gave this explanation that the reason I decide this proportion to be a population proportion simply because it was given without knowing a definite sample size given. And I had students arguing with me that, but wait a minute, isn't it 40 college students is the sample size? So I provided further clarifications as following. This beginning description should be independent with any of the question, because when I delivered this problem, I could have just simply showed the beginning description without displaying any of the questions written here. So without the question, any of the question of part A, part B, and part C written here, then this beginning description is completely independent with that information regarding the sample size. So in other words, my point now is that still, this proportion, once it's given, we only know, we take that fact, somebody did the work to find that proportion for us, but in the end, we never knew a finite, a definite sample size at all. So it is still correct that this must be a population proportion. And so here, our population proportion is known. So we have a known population proportion. And really, this is it. This is all for the beginning description. This is all from the beginning description of our beginning population. And so now we're at part A of the example. So after clearly understanding and extracting all the valuable information from the beginning description here, then here's how we starting to look at part A. So part A, let me spend a little time reading the complete description of part A right here. A sample of 40 college students is collected. Find mu p hat, the mean of this sampling distribution of the proportion. Then we want to find sigma p hat, the standard deviation on that same sampling distribution of the proportion. And the third part of this question is this sampling distribution of the proportion a normal distribution? And so let's look at the information one by one right here. But very first thing being described in this question, part a sample of 40 college students. A sample of 40 college students is collected. So collected from where? Collected from this beginning population. So if we're now looking at how this question A is connected to the beginning description, then the reason I always have to label this beginning part to be the beginning population simply because any sample that we picked comes out from that beginning population. And so now a sample of 40 college students. So now as far as a sample, we have a sample size here being 40. So in this sample 40 students, 40 college students, some of them are going for business major. And so we will have some sample proportion. And so, but now keep in mind, what we have here is as long as we can have a sample, then there will be another one. And there will be another one. So let me make a quick sketch right here to describe the situation. It could be that in in some sample, in a sample, the successive count for being business major is only 1 out of 40. It could happen that way. This is perfectly legal to be a sample proportion, a value of a sample proportion. And then maybe we find another sample, 40 college students. We run into a different successive count. It could be 2 of them. And each one of these can happen frequently as well. So the value, so 1 out of 40 is simply a value of a sample proportion. But it could happen in many samples that we might have the same sample proportion, 1 out of 40. And then so in some other sample, out of 40 students, college students, we might find 3 of them, and etc. and etc. And maybe in some samples, we are probably so lucky that 40 college students, we found all of them, 40 out of 40, are all being business major. So these are all the different the different sample proportion values, where we have seen that throughout our discussion on sampling distribution of the proportion. These are all sample p hat value. So any of these is particular value of sample proportion, but we can now generally regard to any of these value as in this case, we're looking at a random variable capital P hat, because any of these can be represented by a random variable capital P hat which stands for sample proportion. And particularly in my style, I use a subscript 40 right here to indicating that each sample of us right here, each sample of ours contains 40 students. So any of these sample proportion value comes out of 40. All right, so in that explanation, in that way of explaining the situation, then now I'm going to officially define my random variable capital P hat 40 to represent this is the proportion. So any value of P hat, capital P hat 40 is the proportion of business major. But only happen in a sample of 40 college students. And that now immediately brings up for us the idea that what we have here is a sampling distribution of the proportion. It's a population. What we have here, to make note again, this is a population. What we have here is a population, as I described throughout the earlier picture, a population of sample proportion values, of p hat values. And that is the reason why now back on my computer screen, we are looking for now, the question is asking us, so in this sampling distribution of the proportion that we now realize clearly its existence, we are supposed to find mu p hat, the center. So we are now going to find mu p hat. This is the average of all sample proportion values. Think about, if we could find all sample proportion values out there, then what we need to do here is we are going to add our first sample value plus the next sample value plus another sample value plus all of them, adding all of them up, and divide by the number of all samples they are. But since finding the mean, the mu p hat, the mean of all sample proportion values in this way is extremely hard, I can now guarantee for everyone that the answer here is 0.3. And I completely bypassed all this work right here. So how do I know the answer so quickly? without finding any of these sample proportions. And one more time, let's look at the computer screen here, but you see a sample of 40 college students is collected, but that's all it said. We did not even know what particularly was the proportion right in this sample, because the idea of the problem now is that we do not need to find any particular sample proportion. We just simply know that once we picked up a sample of size 40 that can give some sample proportion, then that sample proportion of ours is one among the infinitely many other sample proportions. And so there we call that the sampling distribution of proportion. Then now we can find the mean of all sample proportions. And then just now I showed everybody I can quickly bypass searching for all sample proportion values out there, but quickly come up with that mean of all p hat values to be a 0.3. So back to my concern. How do I know to get this question so quickly? So now this is the part where the central limit theorem has a different statement for this. On a sampling distribution of the proportion, then so this is the mu p hat, which is the mean of all sample proportion values, and central limit theorem guarantees for us that mu p hat will always equals to our lowercase letter p once we know it, or if we know it. And so gladly for us, in our case right here, we already knew from our beginning population that in the beginning population being the college students population, then we already had a known proportion for business major. That known proportion was 0.3. We do not need to know how this proportion was calculated. All we need to know now is that once we have this as a known proportion, then we can use that directly as a result so that we can quickly find out the mu value, the mean of all sample proportion in our sampling distribution of the proportion here will be exactly equal value with our known proportion. And so in this case, consequently, that's why our mu p hat in this case is equals to 0.3 as our final answer. And so once again, all this, what guaranteed this result for us here, came out from another statement in the central limits theorem. And of course, finding mu p hat, or the population mean value on any sampling distribution, is so important at this point of your learning, simply because this is the center. This is the center of our sampling distribution of the proportion, of the current sampling distribution of proportion that we're currently working with. And so now back to question A again. The next part after finding mu p hat, now we are going to find sigma p hat, the standard deviation of our current sampling distribution of the proportion. And so now that we have found on this sampling distribution of the proportion where our sample is one member of, we already found the center of our sampling distribution. So just as usual, we now need to look for standard deviation of all sample proportions. And once again, for standard deviation, we use a sigma here, is indicating that what we have here is a population of sample proportion values. So this standard deviation here makes sense to be a population standard deviation. And the subscript p hat here is indicating that this is the average spreading of all sample proportion values. Because once we found the center, then on average, we want to find out on average how all sample proportion values are spread away from the center. And so, of course, once again, it is impossible to find all sample proportions out there. And so, central limit theorem, thankfully, also has a statement that allows us to quickly come up with this value without searching for all sample proportion values out there. So all we need is from our known population proportion that we already had. All we have to do is from that known population proportion, we are going to multiply, so 0.3 is our known population proportion. We are going to multiply with, in quantity, 1 minus 0.3. And this product is to be divided by 40. This is our sample size. So I need to note again that our sample size in any of these samples is 40. And then after this math work is done, one final operation, we're going to take this answer, this quotient, inside a square root. And so final calculation comes out to be in 4 decimal places, 0.0725. And so as far as calculation and the decimal expansion, then usually I go with 4 decimals. But once again, be watching out for different rounding requirements anytime that you are doing your homework on for the online assignments or for any kind of assignments being given to you. And so where did this formula come from? Or actually we must have seen some kind of setup in here. So let's formulate what formula happens here. So the work that happens here is that central limit theorem allows us to quickly find the average spreading or standard deviation of sample proportions, of all sample proportions, by doing this handy formula. From where our known population proportion is, we're going to multiply p with 1 minus p. So this is a product, p times 1 minus p. And then that product is to be divided by the sample size. And we are going to take that a final square root. So this is another result being guaranteed by a statement in our central limits theorem. So our central limit theorem has another statement that guarantees that we can do this. And eventually I'm going to summarize it all, and I'm going to put on screen what the central limit theorem for a sampling distribution of the proportion looks like. But so the role of this sigma p hat now is, once again, this is the what we have found here for our sampling distribution of the proportion. This is the average spread, the average spreading of all sample proportions. Once we have got center, then this measure on average how much all sample proportions are spread it away from the center. And here is the next part of our part A, of our question in part A. Is this sampling distribution of the proportion a normal distribution? So the wording, simply just staring at the wording, is not telling us much, but this is what it's intended for. So now we realize that we're on the sampling distribution of the proportion, where there are 40 college students in each sample. And we already defined a random variable capital P hat 40. So simply the question stated on the computer screen is symbolically the following question. Is it true or not, or is it yes or no, that our sampling distribution capital P hat 40 would be normally distributed? If it would be, then it would take center at 0.3, as we already have found, and average spread 0.0725. So both of these, the set information, the center and the average spread, were found previously. And so this is the question here. Is it true or not that this sampling distribution of the proportion capital P hat 40 is normally distributed or not? So the answer for this is simply a yes or a no. And we are going to spend some time finding out how we can say yes or how we can say no to a question like this. So primarily here, since we already found center, we already knew center of our distribution, and we also knew the average spread. The primary concern here is what would be the shape of this sampling distribution that we're currently having here. Can this distribution shape be the nice bell curve shape of the normal distribution? And so now, here's my argument. I would say yes to this question. Here's my reason. Now, we already had a known population proportion, and I constantly leave this here. I permanently leave this here throughout our example so far. And so, and the sample size we are currently using is being 40. And I'm trying to give the explanation of how I came up with the answer yes for this question. But so, from where our sample size is, I am going to multiply with 0.3. So this 0.3, remind yourself that it was the known population proportion. So multiplying the sample size with the known population proportion, we came up with a count being 12. What's important is that this count, after we multiplying the sample size with the known proportion, this count is greater than 10. And further, the same sample size that we're currently working, 40. Now I am going to multiply with the following setup. 1 minus 0.3. And again, 0.3 came out from our known population proportion. But instead of multiplying by 0.3, I multiply our sample size that we're using in each of our sample with the setup 1 minus 0.3. And I am going to get another count. This time, calculation comes out to be 28. This count right here also gave me a number greater than 10. And so that is the reason that leads me to make that conclusion that, hey, my sampling distribution, capital P hat 40, is legally on a bell curve, normally distributed with center at previously found 0.3 and average spread previously found 0.0725. So we put a check here. So here's the reasoning for the work that I did earlier to explain how I decided yes for my sampling distribution capital P hat 40 to be on a bell curve here. Generally speaking, from where our sample size is, we multiply with the known population proportion. If this product is greater than, if this product gives us a number greater than or equals to 10, and also besides that product, there's another product, the sample size multiplied with the setup 1 minus P, and remind yourself constantly that P means our known population proportion. So we take the product between our sample size and P, and we also take the product between our sample size with 1 minus P. Both of these, as long as both of these give a count greater than or equals 10, then the sampling proportion, the sampling distribution of the proportion at sample size n right here will be for sure on a normal distribution, on a bell curve, taking center at mu p hat that we found previously, and average spread being sigma p hat that we calculated previously. So I actually just now wrote down the statement that's being guaranteed in all this reasoning right here came out from the central limits theorem as well. All right, so everything that allowed me to move on through part A of our example 1 came out from the central limit theorem part 2 right here. So let me have everybody's attention on my computer screen right here. And let's quickly spend a minute or so to read and understand the central limit theorem, namely the CLT part 2. So for samples, so at this point anyone is well aware that we can have, anytime we pick a sample of size n, there are infinitely many samples. So for samples of size n selected from a population with a population proportion lowercase letter p. So this is indicating that we always need to have, a lot of time we start out, our central limit theorem start out by assuming that we have a known population proportion. Then the sampling distribution capital P hat sub n has the following properties. So statement number 1, the center mu p hat must equal value with p. So we can bypass. So this central limit theorem part 2 right here allows us to bypass searching for all sample proportions, but can still quickly find the average of all sample proportions in our current sampling distribution of the proportion, because that final calculated result is simply just p. In the same statement number 1, but another important result. So average spread, or sigma p hat here in our current sampling distribution of the proportion, can be found quickly by going through the formula p times 1 minus p divided by n, and take all that inside the square root. So the entire statement number 1 of the central limit theorem back on my writing board, that statement number 1 allowed me to come up with center and average spread on our current sampling distribution of the proportion capital P hat 40. Then the next statement in our central limit theorem part 2, there's only one statement. So any sampling distribution of the proportion capital P hat sub n becomes a normal distribution centering at mu p hat and sigma p hat if it satisfies the following requirements. So these are two statements, but need to be two requirements that need to be satisfied simultaneously. And once those requirements can be satisfied, then this sampling distribution of the proportion will be a normal distribution. And that was the reason why when we were answering our last question in part A of the example 1 here, then I was able to make my answer as a yes, and here was the reason again, where my sample size being 40 in each sample. So 40 multiplied with 0.3 gave me a count being 12, greater than 10. Satisfy the requirement stated in the central limit theorem. And then the same sample size multiplied with the setup 1 minus 0.3. That gave me a count being 28, above 10 once again. And so, since both of these requirements are satisfied, I can now say yes to the question. And now I have to make a closing note on this problem part A right here of our example 1 before we move on to the next problem. But so, according to the central limit theorem part 2 right here, then it only gives us the requirements we need to satisfy in order to say yes. As for any sampling distribution of the proportion can be on a bell curve or not. But failing one, so if one requirement, so if any one of the requirements fails, so let's put ourselves into the worst case. If any one or even both of the requirements fail, definitely we cannot say yes. So we can't answer yes for the bell curve setting. But we still can't. Answer know as well. So it just, again, if any one of our requirements here fails, then we just simply do not know what the shape, the distribution shape of our sampling distribution of the proportion is. Simply just that. If we really need to say yes or no there, then we have to find other ways. We have to maybe build histograms or find other ways to find out the distribution shape. But so at the bottom line, as a bottom line here, if any one of the requirements fails, then really we do not have enough information to determine, and determine, I mean to determine the distribution shape All right, so now we are at part B of our example 1. The statement of part B is asking, find the probability that less than 16 is in business major. So before we go on any further, I have to make clear that this question of part B is actually connected to the question in part A of our example. So in part A, we picked a sample of 40 college students. And for that reason, we want to find out that in this sample that we picked, what's the chance that the count of those business students, those business major students being less than 16. And so once again, question B and question A, part B and part A of this example, of our current example 1, are connected. So now back on my writing board here. So once we picked up a sample of 40 students, as I indicated in part A, then we already realized that we had a sampling distribution of the proportion, and namely as a random variable, it's the capital P hat 40. In this entire explanation, this labeling, this description of our random variable, everybody is familiar with already. This is a population of sample proportion values. And I also did a little sketch earlier that, let's say in some sample, we are so unfortunate, we might run into no sample, no business major at all. And so that's the count being out of 40. In some other sample, so this is a sample proportion value. In some other sample, we might find one sample, one business major students out of that 40. So this is a different sample proportion values. And in some other sample, we might find 2 out of 40. And in some sample, we might find 15 students being in business major out of 40 of them. And then 16 out of 40. And then we could be so lucky that sometimes in some sample, 40 students, we found all 40 students being business major. And so back to the question and these are all values. These are all different values of our sampling distribution of the proportion. So these are all different values where I generally regard to that as a value of the capital P hat 40. So capital P hat 40 as a variable can take any of these values. And so for now, I put these sample proportion values as fractions out of 40. So you can understand the situation here. So how is this information here? How is this quick sketch of mine connected in the question? The question wants us to find the probability that less than 16 is in business major. That means, see, clearly realizing that we can have so many different counts out of 40. So how likely is that? What's the probability that anytime we picked up 40 students, 40 college students, our count in the sample there is being less than 16? So less than 16 means we're including the chance of having these counts anywhere 15 or less. So symbolically speaking, I'm looking for the probability in parentheses that my events here is the random variable capital P hat 40 is being less than 16 out of 40. That's how I'm formulating my question. And this question here apparently is a probability question, as it said here in the question, in the statement here. Find the probability that less than 16 is in business major. And of course 16 connected with the information in part A, 16 out of 40 in our sample. And further, 16 out of 40 as a decimal is, so I'm rewriting that symbolic statement. We're looking for equivalently P hat out of 40 is being less than 0.4. So directly from the wording of the question, then we are looking for the probability where our random variable capital P hat 40 takes the count less than 16 out of 40. But that also means equivalent. That is equivalent with saying that we're finding the probability where our random variable capital P hat 40 is less than 0.4 value. So now let's look back at what we already knew regarding our sampling distribution of the proportion capital P hat sub 40 right here. We already knew that this sampling distribution is on a bell curve where center is at 0.3 and average spreading is 0.0725. All this known information came out from answering different questions in part A of our current example. And so now the real usefulness of coming up with this distribution shape right here, and we already approved that, and we've got center of the bell curve, we got the standard deviation. The whole point of doing this is that now we can once again think about all sample proportion values existing in this sampling distribution of the proportion. And all of those sample proportion can exist on a nice bell curves. And this horizontal line once again is where we can find all sample proportion values from low to high, from the left to the right. So we can place all sample proportion values on a horizontal line. And then on that horizontal line, there is our distribution, there is a bell curve. And so the center of this bell curve now is known to be at 0.3. So this symbolic statement now brings up, this symbolic statement is equivalent to a graphical interpretation that we are on a bell curve. Our mu P hat is here as the center of the bell curve, and average spread is the sigma P hat that will be noted somewhere. So 0.0725 is to be noted somewhere on this bell curve. And so now clearly anyone who is viewing this video can start seeing that any sample proportion value can be either above to the right hand side of this center on the bell curve, or it can be below to the left hand side of this center on the bell curve. And so back to our question that I wrote down earlier, what we're looking for now is that on this bell curve, among infinitely many sample proportion values, what's the chance that our sample proportion that we picked up, or what's the chance that we're going to find a sample proportion being less value than 0.4? So 0.4 by itself on this bell curve is somewhere to the right hand side of our bell curve. And so, and mathematically, the statements, the event of our probability question is asking for capital P hat being less than 0.4. So that means graphically we have a shading area, a shaded area being shaded to the left-hand side of this bell curve that we're looking at. And so now, all of a sudden, it turns out again that this is just the usual bell curve problem, the normal distribution problem that we have been learning. And hopefully at this point, anyone who views this video of mine is fluent with your particular skill on how to operate on the bell curve. And so from where 0.4 is, I am now going to find the z-score. So 0.4 minus, so 0.4 is the particular value that we would like, that we're looking for. And again, we're looking for being less than 0.4. So 0.4 is sort of like our limit point, our guiding point here. 0.4 minus 0.3, the center of the bell curve. I am going to divide by the standard deviation, 0.0725. And this z-score, this is the z-score for this particular value. Calculation comes out to be in 2 decimal places, which is usually what I take for z-score, 1.38. That means having a sample proportion being below 0.4 in our case here is equivalent to having a z-score being below 1.38 on the standard normal distribution, or this area shaded to the left-hand side of 0.4 would be equal amount with the area shaded to the left-hand side on the standard normal distribution bell curve at the z-score 1.38. And so now to find the answer to this, all I do is to run my LSND program or any equivalent software program out there to aim for finding the area shaded to the left-hand side of where our z-score is. So with our provided z-score, with our found z-score being 1.38, and let's now going to find, and since the left area is also the area we're actually looking for, so now we are ready to find our final answer. So with my LSND program being on screen as well, it gives everybody a quick review of how we operate with that. But this box right here is to enter my z-score 1.38, so 1.38, and I can just hit enter, and the area shaded to the left of z-score 1.38 on the standard normal distribution is now calculated to be 0.9162. And since on our problem it is also the left area, so our final answer here can now be rounded to 4 decimals. And so what it means here is that, and once again, as a percentage, this 0.9162 is equivalent to 91.62%. So what this answer saying is that anytime you search for a random sample of 40 college students, provided that we have a known proportion of college students out there in the population of business major out there among the college students population is to be 30%, then the chance of having less than 16 students being in business major in a sample of 40 students is a high chance, quite a high chance, above 90% right here. This is 91.62% of chance, or in decimal 0.9162. All right, so we are now at question C of our example 1, and this is the last part in our example 1 right here. So question C here is indeed independent with question with part A and B that we have done previously. So let's now spend some time reading through the wording of question of part C in our example 1 right here. So in a sample of 50 college students, what is the probability that less than 20 is in business major? So this part C of our example 1 here is now independent with part A and B, simply because our sample size now has been changed to 50 college students. So now we're no longer working with p hat 40. We are done with that. So for this, we're no longer working with this. And that is the reason why I'm saying that our part C of example 1 right here is independent with the previous part A and part B. However, this part C in our example still depends on the information given about the beginning population. So let's look back at our beginning population one more time right here. So our population, our beginning population was the college students population. We picked different kinds of samples out there. The category that we're aiming at is being business major, and we had a known population proportion. We had a known proportion of business major in this population, which is a 30%, or in decimal 0.3. We do not need to know how this value was calculated, but what we're about to do now is we're going to be making use of this value for a lot of our calculations. And so from this beginning population, we are now going to draw a sample of 50, or select a sample of 50 college students. And so that immediately gives me the impression that the sample size now is changed to 50. And as we have seen, the idea of sampling distribution of the proportion oftenly enough now allow me to start picking up the pace here a little bit. But so we are now going to define a capital P hat with the subscript 50. This is to represent the proportion of business major in a sample of 50 college students. And so this is now a distribution of sample proportion values. Think about, we can pick up a sample, 50 students, but none of them being in business major. This is a sample proportion value, 0 out of 50. In a different sample, out of 50 college students, we might be a little bit luckier, a little bit more lucky. We found one student being in business major out of 50. Or in some other sample, 50 college students, we might find 2, and so on, to the extreme that some sample we can be so lucky that all of them, 50 out of 50, are in business major. These are any different values of sample proportions. And so that once again enforces the understanding that what we have here is a population of sample proportion values. And so now, after going through part A and part B of the example, and plus here we clearly realize that what we have here is another sampling distribution of the proportion, a population of sample proportion values, then it is now, even though not specifically asked in the question on the computer screen here, but it is now our first responsibility to find out where the center of this population is, or namely it's the mu p hat, the mean value of all sample proportion values. Central limit theorem, as we have seen, now guarantee that, and since we're still drawing samples out of the population that we already knew about the known population proportion, then this mu p hat is once again equals to 0.3. So just like that, we're still, as I said earlier, we're still drawing samples out of this beginning population where we already had a known population proportion being of 30% or 0.3. So automatically guaranteed by the central limit theorem, then the mean value of all sample proportions must equal 0.3. And obviously this is here our center of the sampling distribution of the proportion. Then the next thing, as usual, is to look for average spreading of all these sample proportions. How much on average are all other sample proportions being spread away from this found center? And so central limit theorem gives us a way to calculate this. From our known population proportion, we are multiplying with 1 minus 0.3. And we are dividing this product by, this time we switch to a different sample. Our sample size in each sample now is being 50. So I'm putting 50 in the denominator. And after this calculation, we are going to take a final square root. Calculation comes out in 4 decimal places to be 0.0648. And this is once again playing in the role of our average spreading of our sampling distribution of the proportion, capital X, capital P hat, 50. And again, once we found center as well as average spreading, we want to investigate, we want to find out whether or not our sampling distribution, capital P hat, 50 right here, is normally distributed or not at the center and average spreads that we calculated previously. So we want to consider this question, even though it is not specifically required, even though it is not specifically indicated in our wording of part C, but it's always first information, first responsibilities to find out center, average spreads, as well as distribution shape of our sampling distribution before we can answer the actual questions. So keep in mind again that I'm not anywhere currently working with the actual question in part C yet. So back to this question about whether or not our sampling distribution can be on a normal distribution bell curve or not. The answer can be a yes or it can be a no. And so now I'm going to slightly take things off track a little bit, but instead of directly giving out the answer, let's start out with the reasoning for everybody to get comfortable with this. But our sample size we are using is 50. And so what I'm doing now is I'm going to multiply 50, our current sample size, with 0.3, the known population proportion. That gives me a count to be 15. And this count is above 10. So I'm doing this work to follow with the requirements guaranteed by the central limit theorem. But having this count where the sample size multiplied with our known population proportion being above 10 is not enough. We need to verify another one. So furthermore, from where our sample size is, I am going to multiply with 1 minus 0.3. And let's find out what this count is going to be. Calculation comes out to be 35, which is also well above 10. So now, as long as we have these two requirements about the sample size passed, the requirements indicated in the central limit theorem, then from these two requirements together, now we can make conclusion that our sampling distribution at this current sample size 50 right here, so capital P hat 50, will be on a bell curve normal distribution with center at 0.3 calculated previously and average spreads 0.0648. And so now, based on this reasoning, our answer to this is a yes. All right, so now our sampling distribution, capital P hat 50, is now known to be on a bell curve with center 0.3 and standard deviation 0.0648. Then we can officially think about all sample proportion values can be placed on a horizontal line like this, where the distribution shape is a bell curve over it, and the center of this bell curve is at 0.3. And so some sample proportion can be higher than 0.3, some other sample proportion can be lower than 0.3. But from the left to the right, or from low to high, these are all on this horizontal line. This is where we can place all values of our sample proportions, capital P hat 50. Average spreading on this bell curve, bell curve we're working with is being 0.0648. And now, after setting down this foundation, we are now ready to answer our actual question of part C in this current example. So this question is asking, what is the probability that less than 20 is in business major? And so once again, about the quick little sketch I've made earlier. Some sample, we can run into only 0 business major. Some other sample, 50 students, we found 1. Some other sample, we might find 2, and etc., etc. In some sample, we might find 19 out of 50. And then in some sample, we find exactly 20 out of 50, and etc., and etc. In some very lucky sample, we might find 50 out of 50. So there are different probabilities how each of these values happens. So the question here, in the way how the question is looking on the computer screen, once again, what is the probability that less than 20 is in business major? So 20 here means 20 out of 50. But I'm looking for less than 20. That means among these values, I'm looking for how likely to have these counts being 19 or below. So that means formulating the question symbolically, I'm looking for the probability where my sample proportions, capital P hat, any of my sample proportion, capital P hat 50, takes value less than 20 out of 50. And once again, 20 out of 50 has an equivalent expression, an equivalent value, an equal value in decimal. That is the same as probability, looking for probability where capital P hat 50 is less than 0.4. And now the entire reason of setting down this foundation for us, of laying down this foundation for us, is that the only way we can find this probability answer is to look it up on this bell curve right here. So 0.4 is a value again somewhere to the right hand side of the center on this bell curve. And note that this bell curve has a standard deviation 0.0648, and being less than 0.4, so these are all different values from low to high, the different values of capital P hat 50. So now looking for capital P hat 50 being below 0.4, that's equivalent to a shaded area to the left hand side of 0.4 again. And so now we once again realize that what we have here is our usual, what we're looking at here is our usual work on the bell curve on the normal distribution. It's just our usual normal distribution problem now. So 0.4 from where it is on the bell curve, I am going to subtract the center of the bell curve, 0.3, and I'm dividing that difference by 0.0648, and this is going to be my z-score for whatever will finally come out. So calculation comes out for my z-score in 2 decimals to be 1.54. So what it means now is that from where 0.4 is on this current bell curve of the sampling distribution of the proportion, then 0.4 is equivalent to the z-score 1.54 on the standard normal distribution curve. And so the answer to this question, find the probability where our capital P hat 50 taking value less than 0.4, is the same as the probability where we're looking for a z-score being less than 1.54 on the standard normal distribution curve. And that is graphically represented by this area shaded to the left of either 0.4 or 1.54 on the standard normal distribution curve. And so finding the answer to this is simply a matter of running the LS&D program and giving and providing z-score 1.54 when we're asked to. And as I said again, this LS&D program is only my own program. I distributed it for free to my students, but there are tons of web resources out there that does the same functionality. The idea of this program is to find how much area shaded to the left of a particular the designated z-score on the standard normal distribution. And so here with my LS&D program at z-score 1.54, we're looking at, so the area shaded to the left of 1.54 on the standard normal distribution curve is now going to be 0.9382. And since this is going to be our final answer, then this is simply rounded to 4 decimal places. And that is our final answer here as well. And so once again, now the interpretation of this final answer is that anytime that we pick up a sample of 50 students, then 93.82% of times our sample of 50 students will contain less than 20 of them being in business major.